like a jump in logic, or is it okay? Should we give another reason why these two are similar? Yeah, so you could, if you want to, say that, like, if you wanted to say that these are similar, you could say, because that angle is equal to that one, that equal to that one, and they have a common angle there at P. Cool. And if you wanted to make it a bit more explicit, you could say, so you've got PAC equals CDB. To make it more explicit, you could say that's also equal to PDB. And that is dBA, which is dBP. Okay, so now that they are similar, when we get that two triangles are similar, what do we immediately know? Sides of the sides are in proportion. Oh yeah, before we go there, what should you always remember when you write down two triangles are similar? Or when you make it? Always the order. So like, it's not similar to PBD. Yeah, the corresponding points have to be in the same place. Anyway, so sides are in proportion, which means that, okay, so PA over, what's the corresponding side from the other triangle? P, which one? D, okay. PD is PC over corresponding one, which is PB, which is, what's the third one? AC over BD. Okay. Are we done? We're kind of pretty much more or less basically done. So what we do is we take that one and we multiply across. Then we get PA times PB equals PC times PD. And yay. But so what would the last line be? So therefore, that equals that. And so those ratios are equal. Thus, PA times PD equals PC times PD. And then that's the end of your proof. Okay. Now, let's take a step back. Did you guys mind if I erase this? Is it fine? Yeah, sure. Okay. Let's take a step back from what we just proved. Okay, so we just proved that. And there's another way of looking at it. Let's say the circle is fixed, the point P is fixed, and we're just taking a random line through P that goes through the circle. Let's make this E and F. Okay, can you see that this is also PE times PF? Because it's the same thing we just proved. So what's cool is you can take this point and do any line which goes through the circle, and this value, whatever it is the same. Is that cool?
Yes.
Yes. Good. And this is called the power of point P. So the power of the point is this value. You could say, if you wanted to be more explicit about which circle you're talking about, with respect to this circle gamma. Cool. So this value is the power of the point. I can't remember what the notation is, honestly. I think there is notation for it. I don't know it. Cool. Now, I can do these lines going through the circle. What's a special line that I could do going through the circle? Sorry? Diameter? Okay, so you could do, yeah, that kind of looks like a diameter over there. Okay, so we could do that one. Yes, actually, yes, let's do that one. What shall we call the center of the circle? Give it a name. O. O. What should we call the radius of the circle? R. Okay, I'm kidding. We'll do that next time. Okay. O and R. Now, so this power of the point, I don't know. I don't want to like introduce you to notation when it actually turns out to be the bad one. So let's just call it the power of the point is equal to. So if we're in the special case where that COD is actually the diameter. So it's the power of a point is PC times PD. Okie dokie. Now, is there, seeing as I have this point O, and this is R, and that's also R, is there some, let's say the line PD, could I kind of break it up in a way to introduce the point O? How? Okay, so PD you can write as PO plus R, right? Because it's PO and then plus R. Okay, and what about PC? Someone on that side. How can we introduce O into it? Hi. Oh, actually, I'd rather you because I answered you already. Yeah. Okay, so this is PO minus R. So it's PO minus R, PO times PO plus R. You should know what this is. What does it give you? So PO squared minus R squared because of difference of Q's. It's difference of squares, don't listen to me. Okay, so that's cool. So the power of the point, okay, so R depends on the circle. That stays as it is. The power of the point only depends on how far P is from the center of the circle. Which is cool. Which also means if I take another point, let's say over there, which has the same distance to the center, it'll have the same power. Which is cool. So like if I want to know what are all the points which have the same power as P? What'll I get? Circle. So I'll get a circle that goes like that. Cool. You're learning cool stuff?
Yeah.
Nice. Now, okay, what time is it? 7 minutes. Wait, is it 7 o'clock? No, the stuff I wanted to do was not, it's not going to be quick. Okay. Okay. Okay, so homework, well, not really homework, but okay, so there's these lines going through the circle. What's another, so you can make it go through the center, that's a special line. We get this nice formula for the, we get this nice formula which doesn't depend on A, B, and all of that. What's another special line that you can draw through P which kind of goes through the circle. Homework, investigate, find out, tell me next week. Okay, next thing. That is a Greek letter sigma. That's not the best way to write sigma, but that's how I do sigma. Slightly better might be like that. Okay. So this is the Greek letter sigma. That is also the Greek letter sigma. So in Greek we also have uppercase, lowercase, like A and A. So it's the same thing here. So now, uppercase sigma is used in maths for, or to denote sums. Okay, so the simplest case of this is when you have sigma, you have some kind of variable at the bottom. Usually they use I. It can be odd, K, whatever you want it to be. So they would say I equals something. Well, let's make it just 0.